Let's now look at sampling distribution for proportions, one sample. It turns out that anything that we can do for an average, we can do for a proportion, because a proportion is nothing more than a fancy kind of average. The reverse trip is not true. So, remember, for your population in proportions, we're given a population proportion P, and we talk about a standard deviation. Alright, standard deviation sigma, which is the square root of NPQ, or 1 minus P. You don't need to know that actually. For the sampling distribution, we have a mean equal to P, again, just like with the averages. The standard deviation will be the standard deviation of the sample proportion, P hats, and that's equal to the square root of P times 1 minus P on N. Okay, so the sample proportion, sorry, I didn't do that notation first, is listed as P hat, which is your number of items with a particular quality in your sample divided by the sample size N. Right, both X and N are whole numbers, of course, and so P hat is the sample proportion. The P is a population proportion. The true value, just like a probability, okay, like a probability of a head, probability of something, okay, and so the standard deviation of the population sigma will be the square root of NPQ, but like I said, we really don't need that formula, because when we're doing sampling distributions, all we care about is the mean of the distribution P, standard deviation of the distribution, sigma sub P hat. Okay. So let's look at a problem. I know the notation is confusing, but the actual problem doing is not difficult at all. Sorry, I'm looking for my questions. Alright. Alright, I have a theory that 10% of the population are left-handed. In a class of 70 students, 12 are left-handed. What is the probability of getting a sample proportion as large or larger than this, if my theory about the 10% is correct? Okay. So population, P is equal to 10%. Don't need a standard deviation. Alright, sample, and then probability. The sample size of, what was that, 70. I have a P hat there of 12 out of 70. Alright, 12 are left-handed. So let's do that calculation in Excel. Equals 12 divided by 70. 4 places, 1714. Yeah, I'm about to write it down wrong. 1714, much larger than your 10%, right? Alright, so then what's the probability of getting a sample proportion this large or larger, given my theory is correct? So given that P is 0.1, and when I have a sample size of 70. And what I want is to translate that into a statement for a normal distribution. And for the normal distribution, I need the mean of the normal distribution. The mean is P of 0.1. The standard deviation is sigma sub P hat, which I need to calculate. Alright, let's now calculate that standard deviation. Sigma sub p hat, the square root of p times 1 minus p on n. So that'll be, remember this is not p hat times 1 minus p hat, this is p. So the p is the population proportion, which is assumed to be 0.1, minus p 0.9 divided by sample size of 70. Let's go to Excel now and do that calculation. Equals square root of 0.1 times 0.9 divided by 70. And that is 0.3586. Oops. 0.3586. So now we have a limit, a mean, and a standard deviation, even though we have different notations here. Alright, but that's alright. So we're going to translate this into probability involving z greater than some value. Let's draw a distribution. Right, this is a distribution of sample proportions, p hat. The middle of that distribution is 0.1. We want to find the probability of getting between, 0.1714 or larger. We're going to translate this to the z distribution. Find the z value corresponding to that limit. The formula for the z is again the limit, p hat, minus the mean of the distribution p divided by the standard deviation of the distribution, which is sigma sub p hat. So it'll be that 0.1714 minus 0.1 divided by our standard deviation 0.03586. Now we'll go to Excel and do that. So it's equals our limit minus 0.1 divided by standard deviation. That's 1.99. So 1.1714 is 1.99 standard deviations above the 0.1, 10%. Again, it's an area in the tail, so it'll be a half minus the value from the table from 0 to 1.99. And 1.99 will be 4767. Subtract from a half, and that'll leave us with 0.233, I believe. Alright, so the probability of getting the sample proportion as large or larger than I observed in a class of 70 students is about 2.3%, 2%, which is not real high. So maybe my theory is wrong, or maybe the true proportion is higher than 10%, or maybe this is just a rare sample. Okay. Anyway, that's that probability.